continue with the second short talks. So it's a pleasure to present Renata Possobon from UNICAMP. So she's going to talk about classification of foliation via disintegration maps.
Thank you for the invitation, and it's a pleasure to be here. In this talk, my goal is to advertise the viewpoint of tackling disintegration of a measure, considering some structures of the space. So, in a more general way, what I want is to analyze the relationship between the support of these conditional measures and the arrangement of these measures in the space of probabilities. So this talk is based in two works with Christian Rodrigues and Florentine Munch with the same title. So let's start by what I mean with a disintegration of measures. Roughly speaking, it's a way to write a general measure as a combination of probabilities that are given locally. So for example, if I have one space, probability space here, in a partition of this space in a finite number of measurable sets with a positive measure, then I can write this initial measure here that's in the entire space as a combination of probabilities that are supported in these elements of the partition. In a more general way, what we have, it's given a probability space and in a partition of this space in measurable subsets. We use this natural projection that associates each x with the element of the partition which contains this x to write a sigma algebra on this partition. So we say that some subset B on the partition is measurable if the pre-image of the subset is measurable on X, then we have the family of all these measurable subsets as a sigma algebra on the partition. And then we can also write a measure in this partition by the push forward of the measure mu by this projection. So a disintegration of mu with respect to this partition is the family of conditional measures such that all these measures are probabilities in the elements of the partition which are indexed. This map here is measurable, and we can write the measure mu as an integral of this family with respect to the measure on the partition. We don't need to think exactly in the partition, but we can think in the measure supported on the pre-images of a Borel map. So we can take two different separable and locally compact metric spaces and a Borel map between these maps. And here, this symbol is just for say that this measure is a Hadron measure, finite and positive. So we induce a measure on y by the push forward of me with respect to by pi here. And then the disintegration of a measure is this family of a measure indexed in elements of y, such that every measure, every conditional measure is concentrated on the pre-image of y by pi. And we have, again, probabilities. This Borel map, this application is a Borel map, and we can write the measure as a combination of these conditional measures. So we have a uniqueness in the sense if you have another disintegration in which these conditional measures are concentrated on the pre-image of I for every y, then necessarily these measures are absolutely continuous with respect to the initial disintegration. So, for example, if we have a solid torus, we can think in the projection of the first component here, and then we slice it in this vertical discs. And when we disintegration with respect to this application here, we have one measure on each disk in the torus. Or for example, if we think in some flow, In the torus given by this, we have this closed curve here, and then we can associate it for different points in the square here, different closed curves, and with disintegration in different trajectories. With this notion of disintegrations, we define a disintegration map just by this F that associate each point in Y with the respective conditional measure. But we are looking for these measures in this spatial space here that is called the Wasserstein space. So what is the Wasserstein space? The idea of this space comes from the optimal transport theory. So we can think in this logistic problem that was proposed by Monge, where the idea is to transport masses from a location to another one. So imagine that I have, for example, a pile of sand that I want to transport from here. So I can use some measures to modeling this. So I have one distribution here, one here, and I know how much I need to use to transport these masses. So how we can do it with a minimal cost. So this is the called Monge problem. So given these Hadron spaces and the probability measures and the cost function, we want to minimize the total cost here in such a way that we are transporting the entire amount of sand to the hole. So we need to have these transport maps. This is not a well-posed problem, since we may not have these transport maps. For example, if I have a Dirac mass and another measure is not a Dirac mass, I cannot find a transport map. So what should I do to relaxing this problem? We can think in split masses. So now forget about the transport maps, and now we think in transport plans. We think in a measure in the product space in such a way that this measure tell you how to distribute the mass. And then we look for the total cost among all these transport plans. What you need to check that the initial amount of masses and the final one is preserved. So we look for these marginals in X and Y. You need to have the same measures that we will start in your problem. So all the transport plans that have these marginals, we put in the set that we call it a admissible set. And now we have a problem that is well posed, since at least the tensor product lies in this admissible set. So now our problem is called the Monge-Kantorowicz problem, and then we want to minimize our cost looking for these probabilities on the product space. So the idea of the Wasserstein spaces came from this problem. So imagine that you know your cost, and the cost is a power of the distance here. So the Wasserstein distance is just the solution of this problem, considering this cost. We have a problem here because this is not a proper distance, because we can have an infinite value for that. So what we do is define the Wasserstein space. The Wasserstein space is the space of the measures with p moment finite. So with this, we have the finiteness in the distance. So when we I forgot this. We have some interesting properties, especially when we look for the one Wasserstein space, this two Wasserstein space. The one Wasserstein space is easier to bound in a general mode, and the two Wasserstein space captures really well the geometry of the space X. And here we use this fact that the Wasserstein distance metrizes the weak convergence in the Wasserstein space. What does this mean? When I have the weak convergence, this is equivalent to have the convergence in the Wasserstein space, the Wasserstein metric. So when we back to the definition with this integration map, now we are looking for these measures in this Wasserstein space. For example, a very simple example is this square. When I have this kind of a vibration here, when I just are considering the projection on the first component here, then what happened? It's more or less the same thing with the torus, taking the two-dimensional Lebesgue measure here. When we disintegrated, looking for this map pi here, we have one Lebesgue measure in each fiber. So our disintegration map is just the measure that takes points in 0, 1 and associated with the Lebesgue measure on the fiber x01. Good. So we want to explore more this idea of a fibration. So for this, we define what is a foliation in the sense that is just a partition of X into closed subsets. And then we call a metric foliation these subsets that are parallel in some sense. So if I take two leaves, the distance between these two leaves F and F prime is equal to the distance of X in F to F prime for every X on F. With this notion of a metric measure foliation, we can think in a quotient space, saying that two X and X prime are equivalent if and only if they are in the same fiber. And then we are going to use this quotient space in the quotient map and the distance between two points in this quotient space given by the distance for these pre-images of y and of y prime. If we have this notion of metric foliation with the plus, that also when we disintegration in this metric measure foliation, we have equality between the distance of the conditional measures and the distance of the leaves. We call it a metric measure foliation. For example, in the square, we have this condition of a metric measure foliation since the Wasserstein distance for every p is just the distance between the leaves. Exactly. We can prove with this definition that if I have a p metric measure foliation, then our disintegration map is continuous. Here I use this wiki continuous just to say that it is continuous using the Wasserstein metric. So the wiki comes from this idea, the continuity in the wiki convergence. And this idea of a continuity of the disintegration map also appears in another context. For example, if we put some more hypotheses on y, like for example, this is a manifold with the notion of a volume measure, and our measure nu, it's absolutely continuous with respect to this volume measure, then we can prove that F is continuous in a compact subset of y, because of this is nearly wiki continuous here. And also if we have this pi bijective and the inverse of pi is continuous, then we also have this F, this disintegration map, absolutely continuous, not continuous. What do we do with this continuity of F? One thing is to write paths of measures. For example, if we consider this scenario where f is continuous and y is path connected, for every 2 points y and y prime, we can find a path of measures given by the disintegration map in the two Wasserstein spaces. If we put a little bit more hypotheses, for example, X as a smooth compact Riemannian manifold, a measure mu here that is absolutely continuous with the volume measure, and the pre-images of Y here with positive measure, then if we have our disintegration map here minimizing invariant, what means that it maps geodesics to geodesics, then if one of the endpoint measures in this path is absolutely continuous with respect to the volume measure, all the measures in the path also are. And if this happens, in the case of the metric measure foliation, we have this absolutely continuity with respect to the measure on the fibers and not in the entire manifold. So all this is just to think in this support of conditional measures and the relation with the arrangement of these conditional measures in the Wasserstein space. To do it more properly, we will define a sense of a notion of a derivative. So in the same hypothesis that we started, and always taking f as a disintegration map, we can define it as derivative of the disintegration map as the limit of the supremum in a neighborhood of y of this Wasserstein space between the conditional measures in 2 points in this neighborhood divided by the distance of the supports of these measures. Thinking this notion of derivative, we introduce a kind of energy functional that is just the supremum of all the values of these measures for every y. This idea of this energy functional gives to us one way to classify this kind of foliations on X. So what do we have? That in for X locally compact, completely separable in geodesic space, we can have different disintegrations. And if we take one disintegration map in this space and our energy value is 1, then we have the pre-images defining a p metric measure foliation in our space. More than that, we can conclude that the energy minimizing for the disintegrations maps are always associated with this disintegration of measures. Here we are putting this hypothesis that the measures are fully supported, and this is fundamental for us since we can have cases like this when I have R2 with foliation that is given by ellipses centered on the origin, but the measures, it's really hard to see here, but are just direct measures in these positions here, here, here. So we have the same distance between the leaves and between the measures, but we do not have this metric measure foliation. What do we do with this? So this energy is sensitive to the formations or perturbations in the foliation. For example, with thinking dynamical systems and the evolution of these foliations, when you have some flow and we start to working in a disk on R2 and some distribution there, what we do is looking for what is happening when I'm disintegrating and I changing my measure mu here by this flow. So for example, if our flow is some spiral flow to the orange, so with the time what will happen, it's the point in R going to the origin with the spiral here, or something that is more or less the same, but it's not going to the origin, but for this line here, or just in some vertical compression. What happened with the disintegration in these different cases? In the first one, what will happen is just this radial contraction combined with the angular rotation. So basically what we do is shrinking all this structuring. So nothing happens, just that nothing happens more or less as it's contracting, but the structuring for the disintegration is preserved. So along the time, we have the same energy for every time. Different what will happen with the vertical compression. So we start with this concentrical circles, but then this is turning into ellipses. We can calculate it, what will happen with the disintegration time, and this energy is sensitive to these deformations on the foliation. So calculating this, for example, for the one versus time space, we have this smooth variation in the energy. So the idea here is applying this notion of energy to classify foliations, and more than that, to feel when you have some kind of perturbation or deformation or small perturbations in foliations that are very regular in some sense. There is a lot of things to explore using this framework. For now, you're looking for the regularity of the disintegration maps, especially exploring different ways to define this derivative for the disintegration maps. And with this framework, it's very important to us to define this notion of a gradient, Laplacian, and harmonicity of the disintegration maps to classify different structures on the space X. So this is what we're doing now. Thank you for your attention.